Today we're going to discuss molecular and convective transport. In this, let's first discuss what is Newton law of viscosity. We are very much familiar with what is Newton law of viscosity. That was tau yx is minus mu dux by dy. At a microscopic level and at a macroscopic level, its force per unit area is mu velocity by y, where this is your flux, this was your velocity gradient, and this is your transport property. Then we have a second law which basically deals with the energy transport, that is your Fourier law of heat conduction. Now for this, let's consider two slabs, two parallel plates which are having a distance y apart. Now initially both the plates are at temperature T naught. Let's say initial temperature is T naught and both the plates. Now suddenly the lower plate is brought to a slightly higher temperature T1. The lower plate is brought to a slightly higher temperature T1. Now according to second law of thermodynamics, what will happen? There will be an energy transport from higher plate towards a lower plate. And this process will continue till a steady state temperature distribution is developed. That is, if we plot a graph between the temperature profile and the distance between the plates, then at time t equal to t1, this will be the temperature profile. At time t2, this will be the temperature distribution, and slowly under steady state condition, there will be a linear temperature distribution between both the plates. So we can say that the flux in the y direction will be nothing but minus k dt by dx. Clear? Now this is your Fourier law of heat conduction. Now y represents the direction in which the flux is moving. That's the direction of your flux. And negative sign represents the heat is actually flowing in the decreasing temperature direction. Decreasing temperature direction. Or at a macroscopic level, we can also represent it as heat transfer rate per unit area is nothing but K times the temperature difference between both the plates separated by a distance y. So we can say that this is your energy flux and that's your transport property, and this is the temperature gradient. So this is all about your Fourier law of heat conduction. Then let's again consider the same parallel plates. Now both the plates are separated by a distance, let's say again y. Now the lower plate is, let's say, coated by a material A. That is over here, the lower plate is coated by a material A, which is having a very low solubility in the stagnant fluid B. So over here there is a stagnant fluid. Let me represent the stagnant fluid. It's a different color. Yes, over here there is a stagnant fluid B. Now over here there is a material A which is coated. Now over here the concentration of material A, the saturation concentration of material A is represented by rho A naught, whereas A at the upper plate is having a concentration 0. The upper plate is 0. Now as the lower plate at time t equal to 0, at time t equal to 0, as the lower plate is exposed to this fluid B, the A will move in the upward direction. A concentration profile will develop because since the solubility of A is low in fluid B, so there will be a linear distribution of the concentration of A towards the upper plate. So if we represent the concentration with the distance, so we can say that initially it is 0, at time t equal to it's a 0, slowly and slowly this will be the concentration profile of A in a stagnant film B at T1. Then this will be T2, T3, and slowly again there will be a linear profile developed under steady state condition. Now that's testing. So we can say that JAY, that is the flux, mass flux, is minus DAV, that is del rho A by del Y, where DAB represents the diffusion coefficient of A in B, that is binary diffusion coefficient, and this is your the concentration gradient, and this is your mass flux at a molecular level. Now at a macroscopic level we can again represent the same equation, which is m mass transfer rate of A through per unit area DAB into rho AY by Y, where this is your mass flux, that's your concentration gradient, and this is your transport property. Now if we analyze all these three, now this is your Fick's first law of diffusion. Now if we compare all these three equations, your Newton law of viscosity, that is number 1, your Fourier law of heat conduction, that is equation number 2, and Fick's law of diffusion, that is equation number 3. That is this thing. If we compare all these three equations, what do we understand from all these? If we compare all these three equations are nothing but they're basically the laws which define viscosity, thermal conductivity, and diffusion coefficient. The fluxes, that is tau yx, heat flux, qyx, and mass flux, these are the fluxes, and the gradients, that is dvx by dy, dt by dy, and d rho a by dy, these are the gradients, and from these fluxes and the gradients, we have a defining equations for viscosity, thermal conductivity, and diffusion coefficient TAB. Or in general, we can represent all these three equations in a form of like molecular flux is nothing but a product of gradient of your driving force into the transport property. So that's the general equation which describes all these three laws. That is Newton law of viscosity, your Fourier law of heat conduction, and Fick's first law of diffusion. Further, now all these three equations are similar, but they are not analogous to each other because their transport properties, that is viscosity, thermal conductivity, and DAB, they have different units. They have different units. So let's try to convert them into a similar units. Let's try to find out the analogy between all these three laws. Now, if you look at your Newton law of viscosity, that is tau yx, it's minus mu dx by dy. Now, can I represent it as minus mu du by dy into multiply and divide by rho av? Clear? So this term, it's nothing but your momentum per unit volume. Clear? Similarly, heat flux Qy is minus k dt by dy. This can also be rewritten as minus k if we multiply and divide by rho cp into T. Now what is this term? This is your, we can write it as energy per unit volume. Energy per unit volume. And similarly, Fick's law, that is JAY, is minus DAB d rho A by dy. Now over here, if we see what is rho A, this term is already your mass per unit volume. Now if we compare, if we see all these three equations, in this term is known as your momentum diffusivity, or sometimes we also call it as kinematic viscosity. This term is known as your thermal diffusivity, and this term is already, it's also known as your mass diffusivity. Now if we compare all these three diffusivities, that is momentum diffusivity, thermal diffusivity, and mass diffusivity, they all have same units. All have same units. So in general, we can write your molecular flux as diffusivity into gradient of quantity per unit volume. Gradient of quantity per unit volume. Further, now let me represent them in a very simple way. Let me write over here, it's momentum, energy, and mass. First is molecular flux. Now, molecular flux in momentum is represented tau yx. In energy, it's qy, and then in mass, it's jy. Transport property. In momentum, it's viscosity. In energy, it's thermal conductivity, and in mass, it's your diffusion coefficient. Gradient of the driving force. It's dux by dy, it's dt by dy, it's dA rho by dy. Now over here we are discussing about mass. We can also represent in terms of concentration. Then we're going to use a molar diffusivity. So that we're going to discuss when we're going to come up with your mass transport. Then the diffusivity. Diffusivity over here, it's your kinematic viscosity. Over here, it's your thermal diffusivity, and in mass, it's already your DAB. Now, what will be the quantity per unit volume? Quantity per unit volume. Quantity per unit volume. Now, quantity per unit volume, over here it will be rho Vx, over here it will be rho Cpt, and over here it's already rho A. These are the different quantities per unit volume. You can clearly see the analogies between all these three different laws with respect to the diffusivity and with respect to the quantity per unit volume. Now, if we take the ratio of these diffusivities, we have a dimensionless number. Because all these diffusivities, they have similar units. So if we take the ratio of these diffusivities, we're going to come across certain dimensionless numbers. So first dimensionless number which we're going to come across is your Prandtl number. Now what is Prandtl number? Prandtl number is nothing but it's a ratio of momentum diffusivity to thermal diffusivity. Ratio of momentum diffusivity to thermal diffusivity, which will be nothing but Cp mu by K. Second dimensionless number will be your Schmidt number. It's the ratio of momentum diffusivity to mass diffusivity, which is mu by rho dAV. And the third is your Lewis number, which is the ratio of thermal diffusivity to mass diffusivity. That is K by rho Cp dAV. Or Lewis is nothing but the ratio of Schmidt number to your Prandtl number. Now, for gases, for liquids, normally the specific heat is in the range of 10 raised to power 3. The viscosity is normally in the range of 10 raised to power minus 5. And thermal conductivity is normally in the range of 10 raised to power minus 2. So for gases, Prandtl number is approximately equal to 1. Schmidt number is also approximately equal to 1, and Lewis number is also approximately equal to 1. Whereas for liquids, the specific heat is approximately 10 raised to power 3. The viscosity is approximately 10 raised to power minus 3. And thermal conductivity is 10 raised to power minus 1. Approximately. So Prandtl number for liquid is approximately equal to 10, in a range of up to 10. Schmidt number 10 raised to power 3, and Lewis number again 10 raised to power 2. So that's the range of these dimensionless numbers if we are dealing with the gases or if we are dealing with the liquids. Further, then we come across convective transport. What is convective transport? Convective transport is something like we could say convective flux. Sorry, convective flux is nothing but your quantity per unit volume times the velocity, because there is a certain temperature difference in case of energy. So quantity per unit volume will be rho cpt. That's the difference, that's the gradient through which the heat will flow. And if we multiply that term with the velocity, with the motion of the fluid, it will give rise to a convective transport. So we can represent total flux your total flux is nothing but your molecular flux plus your convective flux, or we can also say it as your total flux is nothing but your diffusivity times the gradient of quantity per unit volume plus your quality your sorry quantity per unit volume times the velocity. So that's the total flux. Let me represent the total flux, molecular flux and convective flux for all these three: heat, energy and mass. So let me make a table over here. So let me you have type of transport, total flux, molecular flux and your convective flux. If it is momentum, the total flux is represented by pi, which you normally have encountered in your bird book. Molecular flux is minus mu dvx by dy, or minus kinematic viscosity into dy of rho vx. Whereas convective flux, it will be rho vx into the vy. That is the velocity in which direction we are dealing with. Second is energy transport. It's represented by ey, the total in flux. The molecular flux will be minus k dt by dy, or it can be represented as minus k by rho cp as rho cp dt. And in convective flux, it will be rho cpt, the gradient per unit, quantity per unit volume times the velocity. And then the third will be your mass. It's represented by w y, which is minus dab d rho a by dy. That is, I'm basically dealing with over a mass over here. And the convective flux over here, which will be rho a into the velocity in which the direction is considered. So you can see the total flux is nothing but the sum of molecular flux and the convective flux. Now if we take the ratio of these fluxes, let's talk about, okay, before that, can I write like the gradient of a quantity per unit volume? Gradient of the quantity per unit volume, it's nothing but the difference of quantity per unit volume upon characteristic length, because if you see over here, the gradient was basically the temperature difference divided by the distance in all these three cases. So over here, the gradient of the quantity per unit volume is nothing but the difference in the quantity per unit volume by the characteristic length. Sorry for that. Now if we take the ratio of convective flux to molecular flux, let me first close the internet. That's a problem over here. Okay, if we take the ratio of convective flux to molecular flux, can I write it as nothing but, now what is convective flux to molecular flux? It's the quantity per unit volume times the velocity. And what is molecular flux? It's diffusivity times the gradient of quality per unit volume, gradient of quantity per unit. Now if I substitute this gradient of quality by this term, can it be represented as convective flux by molecular flux as characteristic velocity, or simple, let's say velocity, let's not use a velocity, over diffusivity divided by the characteristic length, which is nothing but velocity into length divided by the diffusivity. You can see substitute over here. Now gradient of that will be difference in the quality per unit volume divided by the characteristic length. Now this gets cancelled over here. This quality per unit volume and the quality per unit volume will be over here. So that's cancelled up. It's left with velocity divided by diffusivity divided by the characteristic length. So which is nothing but velocity into the characteristic length times diffusivity. So this ratio is known as your Peclet number. So Peclet number is nothing but the ratio of convective flux to your molecular flux, and which is nothing but characteristic length into the velocity divided by the diffusivity. So if I'm dealing with Peclet number for heat transfer, it will be the length into the velocity divided by the diffusivity. Now diffusivity in energy transport is your thermal diffusivity. And if I'm dealing with Peclet number in mass transfer, it will be the length into velocity divided by the diffusion coefficient. So any quantity, its flux can be represented as either molecular flux plus convective flux, or it can be convective flux, subject to condition if the Peclet number is less than 1, subject to condition if the Peclet number is 1, and subject to condition if the Peclet number is much greater than 1. So that's it with the molecular and convective transport in terms of the fluxes. So I hope, if you have any doubt, you can ask me through mail or through WhatsApp, or even you can call me. Thank you so much.